So since the last exam in the differential equations book, we started with section 1.6 or 7, one of the two. Well, essentially phase lines and bifurcations was the first subject. Phase lines and bifurcations was the first subject that we had after exam 1 in pure differential equations. Phase lines only apply to autonomous equations. You can only make phase lines for autonomous equations where the right-hand side has no t's. Don't try to make a phase line for a non-autonomous equation. You can still make slope fields. But the point is with autonomous equations, slope fields are constant along horizontal lines, so sort of squishing the information to the y-axis makes sense. And with bifurcations, you've got some parameter. Often in the book, it was called A or alpha, but I usually call it mu. Whatever you call it doesn't matter, just use some letter. And with in-class exams, I usually just focus on the quadratic examples, where to find bifurcation values, you use the quadratic formula. Why? Why does that work? Because what you're after changes in the number of equilibrium points. Equilibrium solutions in a slope field. In the slope field, there are horizontal lines, constant functions of t that solve the differential equation. The slope field is horizontal along those. Those correspond to points on the phase line, squishing all that information to just the y-axis. We think of them as points. You're setting this equal to 0 and solving for y to find equilibrium points. And with quadratic examples, sometimes you have 0, sometimes you have 1, sometimes you have 2. But with higher degree examples like cubics that could maybe show up on the take-home, you could have 3 equilibrium points. If it was a quartic, 4th degree, you could have 4. If it was a trig function, you could have infinitely many equilibrium points. Yikes. They all often alternate between sinks and sources. This would be a source. This would be a sink, but they don't have to. This could be a node here. If this were the graph of the phase line, what would the graph of F look like? I'm purposely not going to draw a vertical axis because I haven't given a scale here. But where these values are. This is like a y-axis here, but the horizontal axis is like a y-axis there when I'm drawing F. If it's a node with upward pointing arrows on either side, the output of F has got to be positive on either side of that first node. And again, the equilibrium points correspond to where F is 0. This point corresponds to this node here. Again, I made F positive on either side because I got upward pointing arrows on either side of this node. But if it's a node, it's just got to touch the axis and not cross it. This one's a sink. It's going to cross it with a negative slope, as in the linearization theorem. The slope there is negative. That's enough to say this equilibrium point is a sink. This point corresponds to the sink there. And over here with the source, you got a positive slope. That corresponds to this. So going back and forth between these graphs, in general, you should be able to do, even if it's not a bifurcation, for example, you could actually solve on the in-class exam. I'm talking about just the idea here of these graphs. Should be able to think about linearization. This one's got a negative slope corresponding to the sink. This one's got a positive slope corresponding to the source. Linearization does not apply to this one because the slope is 0. But you can still tell it's a node by looking at the graph. There are some special cases where linearization doesn't apply even when the graph crosses the axis, but if it crosses with a 0 slope. Technically, with this example, linearization does not apply because the slope is 0 there. But you can tell by looking at the graph that the phase line would look like this, and it would be a source. Because when you are to the right or to the left of the equilibrium point in this graph, f is negative, so dy dt is negative for the differential equation, and solutions have to decrease. And when you're to the right of it, f is positive, so dy dt is positive in the differential equation, and the solutions have to increase. You got to be able to go back and forth between vertical y-axis here and horizontal y-axis there. I was doing that in my mind as I was saying those things. As far as more general bifurcation values, you know, mu could be an additive constant, and these graphs could shift up and down. Those are the simplest kind. Mu doesn't have to be an additive constant. It could be multiplied, like if this were a cubic, it could be multiplied by the y, which makes the transformations harder to understand. But essentially, you're kind of looking for places where you get this kind of behavior, where the graph is just touching the axis to find bifurcation values. I do talk about that in the lectures. You effectively not only want f mu of y to be 0 at bifurcation values, but f prime mu of y to be 0 at bifurcation values. Both of those equations are going to be true at this point. I'm imagining mu as being a parameter that changes this graph as it changes. You have to solve effectively the system of typically nonlinear equations, which means you need technology to do it. In Mathematica, probably nsolve is the best thing to use. I'm thinking about the take-home here. Possibility for the take-home. What else? We had some symbolic techniques in chapter 1. Method of undetermined coefficients. Effectively, that's a fancy name for educated guessing. Method of undetermined coefficients is a fancy name for educated guessing. Yes, there are undetermined coefficients that you have to solve for as well, so it makes sense still. We use this for linear equations. A general linear equation, first order linear equation, is typically written like this at the start. A of t and b of t don't have to be linear functions. By a linear equation, you mean linear in y. This is your f of ty function. It's not necessarily autonomous. So you would not necessarily want to make a phase line for this, though you could make a slope field. But if it's linear in y like this, with first power of y, and yeah, there's a constant term, so to speak, there. Not really constant because it depends on t. So it's not quite like a linear transformation, but it's like a linear function of y. That's the form of a linear equation. And with the method of undetermined coefficients, very quick summary of it is you want to consider the corresponding homogeneous equation, where effectively you take the b of t to be 0. It's not the same as the original differential equation. It is a new equation. You solve this either by guessing if a of t is a constant. If a of t is a constant, you would get an exponential solution. Or if it's not, if a of t is not constant, you'd want to separate variables to find yh. And then you also want to find the yp, the particular solution of the original non-homogeneous equation. But when you do so, it's better to write it in this form, dy dt minus a of ty equals b of t, because that helps you guess. When you write it in this form, it leads to your yp based on the form of the b of t function. Simplest case is a of t is a constant. And then you're guessing based on b of t, like if b of t is a trig function, you'd guess something involving a trig function. Maybe two things involving a trig function, a cosine and a sine, and you'd have two undetermined coefficients. If the simplest thing is when b of t is an exponential function, then you guess some constant times an exponential function. Like if b of t is e to the negative 3t or something, you'd guess a times e to the negative 3t here, because you're looking for a function whose derivative minus a of t times y is e to the negative 3t for all t. So it makes sense to guess an exponential function with the same coefficient of t. We also did examples with polynomials here, like a t squared. Then you'd want to guess a polynomial here of the same power, but allowing for other powers too. You'd want to like have a times t squared plus b times t plus c. And then in the end, to find the general solution of your original homogeneous, non-homogeneous equation, you add these. And then you use the initial condition to solve for any unknown constants. Very quick summary of that. We also had integrating factors. And with integrating factors, you want to think of the differential equation like that. And you want to define your integrating factor mu to be e to the integral of the negative a of t dt. Now I have a negative sign there by the a of t, but it doesn't, a of t could be a negative constant, and so it really could be a plus sign. Mu is not a constant here, it's a function. It's the integrating factor. You multiply both sides of the differential equation by mu, so it's a factor. And the magic of it is it makes the left-hand side easy to integrate, so it's an integrating factor. By essentially reversing the product rule. You've done that before. You just need to review it. You integrate, solve for y. You might want to, in some cases, solve it both ways and see that you get the same answer. That'll be good practice. Then after that point, we got into chapter 2. We started talking about systems of differential equations, vector fields. How is it related to a harmonic oscillator, like we talked about earlier? With the linear algebra, the pure linear algebra, since the exam, there was more depth about kernels and images of linear transformations defined by matrix multiplication. So that involved row operations to reduce row echelon form. I'm going to have you do a nasty one on the test. Maybe a simple one by hand, but if it was a more nasty system, I'd probably just have you use your calculator. But you often need to think about where are the pivots and are there free variables or not. Help you think about writing the kernel in parametric vector form. The image is easy in parametric vector form so far, is you just take a linear combination of the columns of the matrix. A little bit more high level was in the reading on visual linear algebra online was the rank nullity theorem in its simplest form, related the number of columns of the matrix to the number of free variables and the size of the image. Just call it rank theorem. What else? There was just multiplying matrices corresponded to composing linear transformations. There was the idea of inverse matrices that corresponds to inverse linear transformations. There's the determinant. And with square matrices, you only do determinants with square matrices. And in fact, you only think about inverse matrices with square matrices as well. And the determinant being non-zero is equivalent to the inverse matrix existing. And if the determinant is zero, then the inverse matrix does not exist. Same thing with the linear transformation. As an inverse function, it exists if the determinant is non-zero and does not exist if the determinant is zero. There is other stuff about determinants, geometric interpretations for 2x2 matrices. It's related to areas of the images of linear transformations, and for 3 dimensions, it's related to volumes. And then the more recent stuff that I hinted at the beginning of class today with regard to the more abstract ideas of vector spaces. And 16D, it's going to be linear transformations of abstract vector spaces. But our main example of abstract vector spaces that it's not the same as ordinary vectors is function spaces, where the vectors are functions. There are other examples, but our main emphasis is on thinking about functions as being vectors when helpful, like I did back here. Though when you do, you don't want to draw them as arrows, at least not now. You want to just imagine them as just algebraic objects, symbolic objects that you can add, multiply by scalars, and all the properties hold. And with linear transformations, that's the final thing I'll say today. With linear transformations, don't forget the key idea is it's got to satisfy this kind of property. I'm using vector notation here, but the u and the v could be functions when I write this. That's the key property of linear transformations. That's the key linearity property. And it does work even with these more abstract linear transformations that involve functions.